Let's get started, all whopping 9 of you. So today's our last class, and I know you are so excited, so saddened by that. I guess I had a little Freudian slip there by revealing my true intentions by saying you're all so sad that it's at the end of class, but it is our final class together. And so today we're actually going to just cover one thing. We're going to cover the exam. So we're just going to do a review session on the exam. I was originally going to do environmental health and justice today, but then I wrote the exam and I didn't put any of that material on there. And I didn't feel like massively rewriting the exam. So we'll just not talk about environmental health and justice because we've sort of been talking about it throughout the whole semester. So we're just going to cover the exam today, and then you'll have basically the rest of the week till Friday night to do the exam, and then you'll be done. Other than that, you have a discussion board due today, and you have your lab due today as well. But other than that, just got that final exam to worry about. So what is going to be on this exam? It's unsurprisingly mostly focused on climate change. That's the majority of the questions, but because of how constricted for time I am in terms of I have to put your grades in by basically Sunday night, and the exam you have till Friday. I made this exam a little bit different than last time. So there are 34 multiple choice questions. And there are 2 short answer questions. Both short answer questions have about 5 parts to them, so there's basically 5 questions to answer on each of them. So, and I can tell you right now, one of the questions is about climate change, and the other one is about microplastics. So the 2 big topics we covered in the second half of the course. So just to let you know, they're not essays, so you won't be getting them before time. They are short answer questions, but again, one is climate change, one is microplastics. And as I said, most of the exam's questions are really focused on climate change and plastics mostly. So just to give you a heads up on the most important things. I mean, you'll sort of see as we go through the review slides, like how most of them are focused on climate change as opposed to other topics. So, but like the first exam, you got 2 hours to do it. It is timed, so if you start it tomorrow at 10 o'clock, that's cool. But it has to be turned in 2 hours after the fact. It will auto-complete, just to let you know. Same thing with the first one, right? It auto-completed if after the 2 hour time period. But other than that, it said it's going to be shorter than the first one. There's no essays. There's significantly less short answer, more multiple choice. You'll have your multiple choice. You'll have your grade pretty much after you get it, because I'll grade. I'm trying to grade them as fast as possible. Again, just because I have to turn in grades on Sunday. So you'll get your grades shortly after they're done. Now, in terms of your final grade, it's if you sort of don't just as a note. Alrighty, go to that's not tab. If you just sort of don't remember how your final grade is calculated, it's actually set up to calculate it for you in Blackboard, so you don't really need to worry about it too much, but this is how it breaks down. So this exam that you're going to take is worth 100 points, your previous exam is worth 100 points, and those labs are worth 100 points. And you have a pretty good idea of your attendance and participation. If you come to class every time, this should be an easy 100 points. If you've missed any number of classes, it'll sort of go down from there. And I'm only doing this attendance and participation for when we were in class together, right? I can't monitor what you were doing on your own, right? So, you'll have a sort of general idea. And I'll post your grades, your final grades, as soon as I can. Yeah, and then if there's any problems, you can obviously feel free to reach out to me. But that's where we're at. So. And then this is the grading scale. And a final thing I'll make mention of is I always round up. So if you have a 61.1, I'll round you up to a 62. If you have a 95.9, I'll round you up to a 96. So any decimal point goes to you, just to let you know. So if you have an 89.9, you'll finish with an A minus. So just to let you know. But let's get into it. So let's talk about what are the topics, what are the ideas you need to know. much like the first one, these are the topics you need to know, but the reality is, remember, it's not so much about knowing them, it's about how to apply them, right? That's learning, right? So let's dive in. So the first topic we'll talk about is climate versus weather. Remember, weather is what's today, right? What is today's weather like? And I gave you the fantastic quote from Mark Twain. Climate is what you expect and weather is what you get. I mean, that really highlights the difference between them, because weather is short-term patterns of wind, humidity, precipitation, sun, temperature, cloudiness, etc., over short periods of time, hours, sometimes weeks. But our climate is much more expansive, right? It covers extended periods of time, years to decades. So two very different things, right? When you pop on the Weather Channel or you open your app on your phone, that's the weather. But when you open, say, the Farmer's Almanac, if you guys have ever looked at the Farmer's Almanac, I should say, that's like, hey, here's what the predictions of weather are for 2025. That's really so much based on our climate. And so we talked a decent amount about the atmosphere. Now remember, the atmosphere is a pretty simple part of our planet. It's 60 miles tall, approximately, spans from the surface of the planet all the way up to outer space. It is comprised of two gases primarily. So remember, it's 99% oxygen and nitrogen, two of the most important gases in your atmosphere. And remember, oxygen is what we breathe. Nitrogen, it does nothing, which is a good and bad thing, I guess. There are some other trace gases, with argon being the most, and carbon dioxide and other gases making up the remaining 1%. So again, water, the atmosphere is pretty damn simple, which is a nice thing for you guys. Right? But remember, within the atmosphere, there's a layer called the stratosphere. Now, the stratosphere is the second closest layer to the Earth's surface. And the stratosphere has a really important layer called the ozone layer, ozone or O3. Now, you remember that ozone protects us against ultraviolet light. It absorbs about 95% of UVB. Well, I'm sorry, about 90% of UVB, 100% of UVC, and a tiny bit of UVA. But remember, UVB and UVC are the more dangerous types of UV light. UVA is not so important, or not so damaging, I should say. And we care about this ozone layer because it protects us from these mutagenic pieces of light, right? If you get sunburn, you get a skin tan, right? Or you get skin cancer, it's because of ultraviolet light. It's not just because of the sun itself, it's the ultraviolet light coming from the sun. And we talked about a pretty damn important protocol set forth in 1987. This is called the Montreal Protocol. If you haven't read about it, I recommend you read about it from one of these sources just to give yourself a reminder. But remember, the Montreal Protocol established bans on chlorofluorocarbons, CFCs. These are gases found in refrigerants, air conditioners, things of the like. And they were banned in 87, leading to a net recovery of our ozone layer within about 10 years. But remember, as we discussed, nitrous oxide, one of the most potent greenhouse gases out there, is being produced in abundance. And remember, nitrous oxide is an ozone depleter as well. And it's leading to the hole in the ozone layer to actually coming back, as you can sort of see from this graph, right? It was doing pretty it was pretty expansive here. It died down for a bit, and now you can see it's kind of roaring back nowadays. Again, that's not because of CFCs, that's because of nitrous oxide. And remember, the Montreal Protocol is a great example of a really successful environmental global ban on a substance, really successful, except for the fact we simply did not account for how serious nitrous oxide is as a gas. Now, we talked about the variability in Earth's climate. Remember, we took an 800,000 year look. I didn't put that graph here, but if you want to look it up from the slides, you can feel free. But we talked about the factors that naturally make Earth's climate variable. And so we talked about these Milankovitch cycles. These three cycles, which vary on between a 26,000 and a 100,000 year time period, all alter how much solar energy comes to the planet and the intensity of solar radiation at different levels of the planet, leading to different climates. So those are our Milankovitch cycles. And the important thing I sort of always make mention of when I talk about Milankovitch cycles is, remember, this is natural variability, and we've seen this throughout the records, but right now we're simply out of step with what these Milankovitch cycles could potentially do to our climate. Then we talked about two short-term, well, actually one short-term way to make the planet warmer, and that is El Nino. You'll remember that El Nino is a shutting down of these westerly winds. Now remember, La Nina is sort of the status quo, where we have these westerly winds and currents pulling hot air, pulling hot water off the coast of Central and South America, and a little bit of Southern California, over and dumping it on our friends in the Indo-Pacific Islands, as well as Australia, because, you know, obviously Australia is not hot enough, apparently. And remember, this is an important thing because it creates a pocket of warm air here, but what it does is it dramatically cools this area of the world. And because of how large the Pacific Ocean is, confining all that heat to one small area dramatically changes the climate over, you know, a few years' time, but it's not a permanent change, right? And then we have El Nino, which is the not so fun, I guess, brother of La Nina. It's in which the westerly winds off this coast of Central and South America shut down, leading to a pooling of warm water in the center of the Pacific Ocean, as well as along the western seaboard of Central and South America, leading to a much warmer Pacific Ocean. Much warmer Pacific Ocean. And remember, given how large the Pacific Ocean is, any meaningful change in the temperature of the Pacific Ocean over large stretches of it has dramatic effects. And El Nino, when it's in effect, warms the planet by a couple degrees. It's pretty dramatic. I remember when I was a kid, I remember just how serious sort of El Nino was at the time. Just because of how hot it was getting in sort of Central and South America. And then the final thing I'll make mention of, it's not really super important, but remember, when this happens, when El Nino happens, it actually almost completely shuts down the fisheries in this area of the world, which is billions of dollars in economic damages. So it's not just it's hot sort of thing. And then we have volcanism, or just volcanoes. Now remember, volcanoes produce some greenhouse gases, right? We have carbon dioxide. They also will emit some methane, but that's not super duper common. But the big deal that volcanoes do, outside of acid rain and stuff like that, we don't really care about that for the sake of climate. We care about it because it produces sulfur dioxide, and sulfur dioxide increases the albedo of the planet, reflecting more solar energy back into outer space, thus cooling the planet. And, you know, kind of acts like putting like painting your car white. That's sort of the way sulfur dioxide works. And, you know, that we sort of showed you with this. I showed you with this graph from UC Berkeley, where you can see all these large eruptions over time, whether it's, you know, in Central and South America or Africa, where you have, or some island in the Pacific where you have a large volcano, temperature drops by a few degrees for a year or two or so, and then the sulfur dioxide in the atmosphere goes away, restoring the Earth's albedo, making the planet warm back up to what it was before. And you can sort of see like volcanoes come and go, but the projected rise in temperature and the current rise in temperature just kind of keeps on chugging. So it's kind of a, you know, a short-term fix, but not a permanent fix. And again, it's pretty much every large volcano. Fun fact about Krakatoa: Krakatoa was such a explosive volcanic eruption. You could hear it for thousands of miles away. It was so loud. It was like deafening at the time. It's a pretty cool little volcano there. Anyways. Now this brings us to climate change. Now we talked about this in particular curve, this red line. This is called the Keeling curve. You don't really need to remember it, but just to know, like anytime you see this wiggle of a red line through a black line like this, it refers to a Keeling curve when it's looking at CO2 in parts per million. And remember, the red line is the CO2. It's high in the winter. Winter in the northern hemisphere. Remember, that's where most of our land mass is. Most of our trees are in the northern hemisphere. And then it dips down in the summer of the northern hemisphere, so the winter in the southern hemisphere. And we have this back and forth between winter and summer, but you'll notice that the average CO2 in parts per million in the black line goes up and up and up. And so this is where we're at, right? We have rapid climate change due to human activities. Now, the question we can ask ourselves, and we probably should ask ourselves, is how do we know this is human induced? Well, the reality is when you look at, say, this video, for instance, which I would recommend that you do, if you haven't already, you'll notice that the rate at which CO2 changes, i.e. going from 400 to 410 parts per million, that only took that only took 4 years in modern times, right? So the slope of this line is very steep. But when you look at, say, 50,000 years ago, that slope of that line is significantly smaller. So the big deal about climate change is, yes, of course, the climate will change over time. That's what it does. However, remember, the rate at which climate is happening, the climate is changing simply is unprecedented within the past 1 million years, and likely longer, as far as we can tell. And so that's the key for humans, right? In climate change and how it relates to us, it's how fast. Yes, remember, climate is naturally variable, but how fast it's changing cannot be explained by anything on this planet, anything. And that's the reality of it. So that's always an important thing to keep in mind, because one of the things you'll see by either it's propaganda from climate deniers or just climate deniers just being themselves, is that climate change is natural. And of course that's true, but it's always in context of how fast, right? How fast is CO2 changing? How fast is the Earth's temperature changing? Because remember, when we looked at that million-year record, it took 50,000 years to go from 280 parts per million all the way down to, say, 180 parts per million. But it only took us 150 years in modern times. So it's always about the rate. And I'm putting a pretty heavy pressure on this idea because it's important, but it's also because it's on your exam. So just as a note. I wouldn't spend my time talking about something in a review session if I didn't think if it wasn't going to be on the exam, of course. So now we can ask ourselves where are human greenhouse gases from, right? So we know that the greenhouse effect is one of the ways by which the Earth's temperature changes, right? More greenhouse gases in the atmosphere lead to a warmer atmosphere. Now, natural background greenhouse gases are primarily water vapor, CO2, and there's a few others, methane, nitrous oxide. But human, i.e. anthropogenic, man-made greenhouse gases are dominated by carbon dioxide. Carbon dioxide is the most important gas that we produce because we produce so dang much of it. But remember, carbon dioxide is really only part of the piece, a part of the puzzle here, right? Methane, nitrous oxide, and a few other gases do make up a 15% chunk. But remember, the potency of these gases, of this slice, means that slice, while mass-wise is only, say, 15%, it's probably closer to 30% on the sort of overall global effect. But again, CO2 is still the bad boy in town. And we can tie our emissions. Again, we'll ignore sulfate here because it's not important for what we're discussing. But for methane, CO2, and our friend nitrous oxide, they all have a J curve, right? We talked about that classic J curve, that exponential curve that we saw in our population demography class. That follows directly the J curve of human population. And remember, what's fueling this, and I don't mean that to be a pun or anything. I just couldn't think of a better word to use. What's fueling this rise in population is technology, right? Whether it's agricultural, whether it's scientific, whether it's medical, whether it's engineering based, right? It's all fueled by technology, right? This J curve of our population. But to power that technology, it requires fossil fuels, and our fossil fuels emit, as they're combusted in an engine or factory or whatever, they emit CO2. They inadvertently can make nitrous oxide, and they can also lead to the release of methane. So it's what's driving the emissions of these gases, which are in higher concentrations than they ever have been before, is our technology. For as good as technology is for us, again, it's not the best thing for our climate. So where are some of our sources of CO2? So we sort of talked about the combustion of fossil fuels, but remember we talked about fires, and I showed you this awesome picture of Michael Scott from The Office, because everyone loves Michael Scott. Well, except for first season Michael Scott, he was really cringy in the first season of The Office, but every other subsequent season he was awesome. But CO2 has, combustion of fossil fuels is one way, but remember we put precipitous amounts of CO2 into the atmosphere via wildfires. And so 25, in the fires of 2020 in California, or even say the fires that are happening in Siberia, we put substantial amounts of carbon dioxide in the atmosphere as we burn organic material, which is, a concerning thing, right? Because climate change makes forest fires more likely and more intense, which means we put more CO2 in the atmosphere, which makes the planet hotter, which makes fires more likely, right? So it's kind of one of those feedback loops that we discussed in class. Next up was methane. Now, methane has a variety of sources, but remember, the two most common places we produce methane is from our cows. Remember, this comic lies to you. It's funny because like saying a cow saying "pull my hoof" is kind of a funny thing to think about, but it's simply not the case, right? We know livestock, i.e., cows, they produce lots of methane because of the foods they eat, and it comes from their mouth, not their butt. So it's cow burps. And the other big area for methane is our food waste. And remember, food waste produces a crap ton of CO2 and methane on a yearly basis. And I always highlight the importance of this graph and the importance of your own personal choices, because food waste, while a huge dollar value, is also one of the biggest sources of climate change, right? It's the third largest country in the world. If you were to add up all the food waste in terms of greenhouse gas emissions, which is quite staggering when you sort of think about it. And remember, most of that food waste comes from when you go to Chipotle or when you're making a chicken casserole at your house or something, right? That's where most of the food waste, CO2 and methane comes from. So personally, if you ever want to be like, I want to help climate change, try to waste less food. But again, it's kind of hard to battle climate change on your own, right? So. And then we got to our final guy, and as I always mention, is my favorite gas. This is our friend nitrous oxide. It does a small proportion of it, about 10%, is produced via the combustion of fossil fuels. Remember, as you burn fossil fuels, all that intense energy takes all that nitrogen in the atmosphere and makes nitrous oxide. That's not really that important, but that's just as a reminder, that's how it goes. But remember, most of it comes from our agricultural practices, in particular, how we poorly manage our agricultural soils. As we talked about in the food class, the reason our soils, or at least part of the reason our soils are so degraded, is because of the amount of synthetic fertilizers we add. And because of that, the way we treat our agricultural fields leads to more degradation of the fields, but also more nitrous oxide production. And remember, nitrous oxide is an ozone depleting gas, right? So it destroys our ozone layer, making things not so good. So this brings us to this graph, which is the temperature anomaly today. I recommend, if you haven't read it, take a peek at this NASA article. It's very, very similar to what we're looking at here, but it's a really good article about it. And we're at it globally. We're about 1.02 ish. I would argue I would say we're probably closer to like 1.05 in that ballpark. But 1.02 is a good point. And it's all relative to pre-industrial times, right? 1850s, right? Prior to 1850, right? After the Industrial Revolution really kicked off. And CO2 is very, very high. Remember, it's almost double what it was before the Industrial Revolution. And the only way we can explain that is by the combustion of coal and other natural gas, other fossil fuels. I'm just getting ahead of myself. And the other pertinent point to take away from this slide is where warming is occurring. Remember, most of the warming is not spread uniform, right? Some places are cooling, and that's an important facet of it. But you'll notice that most of the planet is pretty much on fire, right? With the Arctic being permanently on fire, and all already really dry areas, whether it's the Middle East or potentially, or even Australia, or some of the drier areas of China, or even just places that are historically wet, like the eastern seaboard of the United States, or maybe the Amazon, are getting warmer faster than, say, other places. So like our friends in North Dakota, for instance, they're not getting as fast as, say, we are, as hot as fast as we are, right? You can sort of see that dichotomy here in the center of the United States versus, say, New England. And so we talked about lots of effects of climate change. Like, what do we expect to see in the future, and what do we see now? Right? There's lots and lots of things. What I would recommend for you is take one of the things. I didn't put all of them. I put some of them. I put a couple of them here, the sort of the big important ones. But there's lots of effects in class that we talked about, and I didn't put all of them there, as I said. But I would recommend, and this is me not recommending it, more so that you should definitely do this for the exam, is I would pick one thing outside of sea level rise. Pick any of the ones you want from the lecture and really get to know that one well before the exam. And again, I'm not saying that you shouldn't do, I'm not saying like you have to do it, but I'm strongly encouraging it. And I think that should be a big enough hint as I can give you about what one of your short answer questions will likely be about, just as a note. So we're going to talk about a couple of these because there's direct questions asking about them. So, but remember, there are tons and tons of effects of climate change. There's about 50 slides, right? So go learn about some of them, pick one and become an expert on it. But one of the more important ones is ocean acidification, right? Remember, as CO2 is produced, about 70% of it dissolves directly into our ocean. Why is that? Well, remember, the ocean covers about 70% of the planet, and the ocean can hold a massive amount of carbon dioxide. So just as a refresher. But what happens is CO2 dissolves into water. It reacts with the water molecules, so as you can sort of see here, and it produces a very weak acid called carbonic acid, thus lowering the overall pH of the ocean by, depending on where you are, by up to 1 pH unit, which is a substantial decrease. And this has a pretty dramatic effect on a lot of things. It affects oceanic chemistry, but the big thing that we talked about is the effects it has on shellfish. So it weakens the shells of lobsters, it weakens the shells of snails, oysters, anything that has a shell, a hard shell, is weakened by ocean acidification. And it also damages pretty severely our corals. Right, so corals, when they're happy, they look like this. And then remember, when corals are stressed, either because it's too hot in the ocean, or there's too much CO2 and it's too acidic, the corals become bleached and eventually die. And so we see the loss of reefs like this, including large parts of the Great Barrier Reef in Australia, which is arguably the largest reef in the world. Also one of the most beautiful reefs in the world, but that's more so an opinion than a fact. And remember, once a coral dies, it never comes back. Like once this happens, the coral's done forever, and it takes hundreds of years for these corals to come back. And the other important things to sort of remember is as coral reefs go bye-bye, as do the fish, which not only are economically beneficial because of tourists and selling them, but also people that depend on coral reefs, which is about 1 billion to 2 billion people on a yearly basis, lose a valuable piece of their diet. Right? So it's both financial and sort of ethical ethical issues as a result of the decline of coral reefs due to more CO2, i.e. the acidification of the water. And then we talked about sea level rise. And so this is what we're seeing for sea level rises. This 0 is the mean over this time period. And then you sort of see our sea level is going up and up and up and up and up. And at this point, we're about +4 centimeters from where we were in that ballpark in modern times. But these are projected to keep going up and up and up and up. And as with the temperature map, the map of sea level rise is pretty dramatic, is pretty unevenly split. Right, some places are getting slightly lower. You can see those are few and far in between, but you also notice that most of the places are getting higher in terms of sea level, and substantially so. And the example I sort of pressed home was, eastern seaboard of the United States, where 20, 30, 15 plus million people live, is experiencing some of the highest rates of sea level rise in the world. There is sea level rise happening here pretty heavily, right? But there's no people living there, right? So it's particularly concerning when you have 100 million people living in one area and sea level rise is going really fast. And so we talked about 2 ways that sea level rise works. There's 2, right? First is melting of glaciers, right? This is what we call meltwater. And remember, it's important that it's landlocked ice sitting on land. Greenland is a great example of that. And why is that important? Well, remember, if you have a glass of water with ice in it, right, and that ice melts, the volume of your glass of water does not change, right? But what does change the volume of your glass of water? Well, if you pour a bunch of melted ice cubes into it, right, that causes the volume of your glass to go up. So just remember, that's a key thing. It's a key distinction, right? We don't care. We care about sea ice, but we don't care about sea ice for sea level rise. We care about landlocked ice, glaciers, Greenland, places like that. We don't care about Antarctica for sea level rise, just as a note, just because it's a giant pile of ice. The other thing we care about is thermal expansion. And this is a pretty straightforward thing. As water gets warmer, it expands in volume. That's pretty much it. And those two things combined, melting of water and the thermal expansion of water, have led to the dramatic changes of sea level rise over time. And we are projecting to see pretty substantial sea levels going forward. I mean, some places are already experiencing them, don't get me wrong, but we expect to see some pretty substantial rises in sea level over time. So as I mentioned, these two, acidification and sea level rise, there's direct questions on the exam about them. That's why I went over them. But remember, there's 50 slides worth-ish of effects of climate change. And as I said, pick one that really interests you, something that you find interesting or you didn't hear enough about, and learn about that one, study that one really intensely. Just don't make it sea level rise, just as a note. So just as a reminder. Okay, this brings us to waste. And so there's a lot of things that go into waste, right? And so we talked about waste, first what hazardous waste means. Now remember, hazardous waste is anything that is potentially dangerous, flammable, explosive, so on and so forth, and harmful to biological life, either humans or plants or animals, right? And we talked about a number of ways to clean it up. So we talked about bioremediation using bacteria. We talked about phytoremediation using plants, where we talked about using badass technologies such as plasma gasification to potentially clean up our hazardous waste. But, oh shoot, this got messed up. Sorry about that. I guess importing it into the slide messed up the formatting. I didn't notice it, which makes me wonder what the rest of the slides are going to look like. Anyways, doesn't matter. And we talked about some other methods, both physical methods like filters to remove them, as well as chemical methods to treat our hazardous waste. But remember, the vast majority of our hazardous waste is simply buried. And remember, that's not a great thing, right? Because, well, it's cheap, and if people are obviously going to choose the cheapest option because that's what businesses do. While it is cheap and relatively effective, we do worry about leaking of our chemicals or hazardous waste into the environment, and that's kind of not a good thing, right? Not a good thing at all. And then the final thing we talked about is our surface impoundments, as well as storage vaults. Remember, storage vaults, they don't really typically look like this, but they use these 55-gallon drums to safely store things and monitor them over time. Remember, that's very expensive, so we don't like to use that very often because, again, money is the name of the game. But the other common thing we see is surface impoundments. We basically have little ponds or sometimes mini lakes, depending on the company, where they basically dump their chemicals in there. They're supposed to be lined, but remember, most of them aren't. And they store chemicals technically indefinitely if they're constructed properly. But remember, most are not, and most have problems with leaking and stormwater and things like that. So those are the ways we handle our hazardous wastes. And hazardous waste, as we discussed, is simply one aspect of solid waste. Now, solid waste, remember, it can be solid, it can be liquid or a gas, so it's technically not always solid, which, again, I know it's a frustrating thing to hear because you think solid waste, it should be solid, but surprise, it's not. Now, solid waste, remember, it's a wide variety of things. It does include hazardous waste, but it also includes other things from industries, wastewater, sewage, as well as your municipal solid waste, i.e. the stuff you throw out, cardboard, food, cans, and so on and so forth, all sorts of things. And so, as we discussed, the United States is #1 per capita and total. 25% of all waste comes from the United States. And I gave you these stupid statistics, right? You could circle the earth 10.5 times with the K-cup sold in 2013 alone. So all sorts of crazy things, because say what you want about the United States, when we do something, we typically go big, right? We may only have 0.4% of the world's population, but we go big pretty hard. And so one of the things we discussed is outdated infrastructure, how solid wastes can make it into the environment and become potentially cumbersome and no, cumbersome is not the word, bad for the environment. There we go. And the first one we talked about, the only one we're going to talk about, yeah, the only one we're going to talk about is as combined sewage outflows. Remember, these are these places that are designed, it's outdated infrastructure, of course. In Boston's, as you guys probably know, is a pretty old city, one of the original cities, right, in the United States, or at least large cities, I should say. But these confined sewage outflows basically have untreated human waste, our poos and our pees, industrial waste and other stuff, and they carry them through things, and they are potentially discharged into the Charles River, but they're supposed to sort of help mitigate the effects of too much sewage. But remember, these potentially leak hazardous waste into the Charles River, the Mystic, or even the Neponset River historically. It's kind of a gross thing. So that's one of our ways we sort of poorly handle things. So that's the sort of the last thing about waste that you really need to sort of remember. And then we moved on to a specific type of, well, actually we did this lecture first, but technically we're just moving on to a different type of waste, or a specific type of waste, which is our plastic. And so remember, our plastics, they affect not just us, right? They affect marine lives. 700 species have been documented to be negatively affected by oceanic plastic. And you have these terrible pictures. And then we have, even more terrible pictures where you see, this one from, I think the World Wildlife Foundation, and actually this one is too. But you can sort of see this sperm whale, it's died, and you sort of see the contents of its stomach, cups and plates and plastics and plastic bags, and so lots of nasty stuff. And so our plastics, remember, they're accidentally ingested by marine animals because they think they're tasty. All right, a plastic bag might look like a jellyfish, might look like a fish, or if you're a giant animal like a whale, you just accidentally gulp it in. Right? So it's lots of ways our friends in the marine waters intake plastics, which is kind of an unfortunate thing. But remember, we produce astronomical amounts of plastic, millions of tons every year, 50% of which is single use. Now remember, single use plastic is you use it once and you throw it away, right? It's your soda bottle, right? It's your if you're a smoker, it's your cigarette butt, right? If you go to Dunkin' Donuts, right, you get your I don't know, styrofoam cup with your coffee in it. That's your single use plastic. And remember, most of the plastic by volume does come from Asia. So the top producer at 80%, if I'm not mistaken, is our friends in China. Not so closely followed by some other Asian nations, Indonesia, Philippines, Vietnam, and so on and so forth. And the United States rounds out the top 20. So lots of countries. And I think it's kind of a good thing. The United States isn't number one. Remember, we are the number one per capita in total amount of solid waste, but we do a better job of handling waste, it seems, or maybe it's a culture. I don't know the reason of handling waste in some other countries, which again is kind of a good thing. Now, remember, as plastics break down, remember, plastics simply do not decompose, right? The example I kept giving you was a sandwich, right? I eat a sandwich. I don't want my sandwich anymore. That sandwich gets thrown away. That sandwich decomposes, right? Something eats it, gets, recycles the nutrients back into the environment. But plastics simply don't do that, right? They break down, they get smaller and smaller and smaller until they are called microplastics, right? Microplastics are things less than 5 millimeters in size. And so these plastics, they get really, really small, but remember, all sorts of nasty things stick to plastics. There's a whole classification of POPs, or persistent organic compounds, that do stick to them. BPA and other hormone mimickers, PCBs and heavy metals, pharmaceuticals, pesticides, flame retardants such as asbestos. Lots of poisonous things stick to our plastics, which can be ingested and cause harm to the organism that ingested it. Could be us, could be a fish, could be a shellfish, doesn't really matter. And all these things have pretty dramatic effects on the biology of organisms. We see reduced food consumption, reduced offspring viability, physical damage, and reduced overall growth of species. So there's lots of not so fun effects for our marine life out there. But one of the things that we concern most about is how it makes it back to our dinner table. Right. So if you eat fish, or if you eat any type of meat for that matter, you worry about how sort of these bad things make it back to your dinner table. And this makes it back to your dinner table via biomagnification. Right. So, and bioaccumulation. So we have bioaccumulation where things build up over time. And then we have biomagnification. And I mean, things build up over time in an organism, right? So as this organism grows, it picks up more and more toxins over time. And then we have biomagnification where it gets more concentrated up the food chain, because a polar bear eats a lot of seals, and the seals have to eat a lot of fish, and the fish have to eat a lot of zooplankton or krill or whatever the heck these are. But as they eat more and more of what's below them, they pick up more and more of whatever's contaminating the water, whether it's plastic or otherwise, leading it to become more concentrated in tissue the higher you go in the food chain. And remember, humans typically eat at the top of the food chain. Right? We typically are eating here, right, in this ballpark. And so when we eat stuff, tuna, trout, whatever, we potentially ingest not a lethal dose. I don't think that's ever been the case, but certainly a higher than average dose than we would want. And so that's our biodomagnification, that's bioaccumulation. That's how plastics potentially, and the things that stick to plastics, make it to your dinner table. It's kind of an unfortunate thing. And then we talked about the effects of human health. So your food you eat is one way you get a sort of smacked in the face by plastics. And remember, what you drink and how you package your food also influences how much plastics you get. But once they get inside you, what do plastics do? And remember, we sort of talked about this as being an uncertain aspect of plastic research at the moment. And, sort of on the scale of, completely false to 100% true, it's more so leaning towards the 100% true aspect, right? So it's not quite there yet, but it's getting there. And so what happens to humans when we consume too much plastic, right? Or the stuff that's stuck to plastic? And the reality is we don't quite have the answer, right? But we know lots of things, including phthalates, which are called plasticizers to make plastics more flexible, durable, more better, basically. They affect growth, they affect metabolism, they affect reproduction, as you saw in the documentary I hope you guys watched. And they affect lots of other things too, development, there's linkages to ADHD and autism. There's lots of sort of things we are associated with consumption of plastic and the things that stick to plastic, but we don't quite have that smoking gun yet. But there is certainly a lot of reasons to be sort of wary about plastics in your life, especially for younger folk. Less so for adults. Adults are pretty good at taking in a lot of toxic crap and dealing with it, but younger folks not so much. So, and then sort of the final thing is actually pollution. And so this is from earlier in the semester. This is from our water pollution, and we'll talk a little bit about air pollution as well. I didn't test you on this yet, so I wanted to bring it back for this class because it really ties in with plastics and it really ties in with waste. So let's talk about pollution. Now, remember, water can be polluted either via a point source. And so if we think about a point source, we have a factory or say a wastewater treatment plant here, and we have, say they have human waste and they're dumping it into a river, and we have contamination with human waste in this water source down here. Well, we know exactly where the human waste came from, right? It came from the factory or the treatment plant here. Thus, that is what we call a point source of pollution. Conversely, if we have something like agricultural runoff, right? Agricultural runoff is sort of, it's not coming from a single pipe, right? It comes from many, many farms, either upstream or downstream. Many points within the farm have the potential to add waste to a stream or any body of water. So we would call that a non-point source of water pollution. And so we talked about Minamata, for example, right? Minamata in Japan was an example of a point source pollution because it was a factory dumping a chemical into the ocean, which led to the problem of the pollution in the water. So non-point sources, we don't know where it's coming from. It's potentially many sources. Wastewater, agricultural runoff is a great example of that. We don't know, the Mississippi River, where there's thousands upon thousands of farms up and down it. If there's any agricultural runoff in the Mississippi River, it's kind of hard to pinpoint where it came from because there's so much farmland along the Mississippi River, which is why we call it a non-point source of water pollution. And then we talked about air pollution. So how does the atmosphere become polluted, right? And commonly we're thinking about, a wide variety of things, but oftentimes when things are burned, right? Forests catch on fire, we burn fossil fuels in our cars, right? Or there's large storms, right? Kicking up things from the dirt, right? There's lots of ways things get into the air. And they're all this variety of things. It can be something as nondescript as sea salt. Sea salt is technically an air pollutant, as is soot from, say, a furnace, right? Or a volcano going kabooey, or pollen from your favorite plant in your house. So lots of things are classified as air pollutants. And we break our air pollutants down into both primary and secondary air pollutants. So the first idea of a primary one is a substance that is harmful, that is directly emitted from its source. So if you have human hairs, for instance, are directly harmful, they're allergens, they're irritants, that is technically a primary pollutant because it's not altered, right? Carbon monoxide from a furnace, also primary pollutant. Dust, beach sand, pollen, ash from a fire, all those are primary pollutants because they are harmful in their standard form. But there's lots of them, lots and lots out there. There's metals, there's what compounds we call volatile organic compounds. There's all sorts of things that are classified as primary pollutants. But remember, the key here is a primary pollutant is something that is emitted and is directly harmful, because that's in contrast to our secondary pollutants, right? Where the product of something happened to that pollutant when it makes it into the atmosphere. So one of the things we commonly see is like smog, right? As smog, it's a contraction between smoke and fog, right? As our smoke from factories and cars makes it to the atmosphere, it reacts in the atmosphere, producing smog, which is a type of secondary pollutant. Because again, it's something has to change to a primary pollutant, making it into something else. Smog is a pretty common one. Now, the common pollutant in smog is a group of gases called nitrogen oxides. Those are relatively common secondary pollutants we see across the planet. So lots of potential chemical reactions. You don't need to remember any of these last slides outside of like specifics. So you don't need to remember, oh, that dust is a primary pollutant. You just need to sort of know the difference between a primary and a secondary pollutant. So, but that's it. This, like I said, this one is mostly focused on climate change, and then a decent on waste and plastics, with a little bit of pollution and a little bit of water as well. But again, a limited set of things. So for those of you that came a little bit late, this is all we're doing today. We're just doing an exam review. This is the format of your exam. I had to email these out for you. For some reason, I can't upload this slideshow to Blackboard for whatever reason. So if you want this slideshow, check your email, your Bentley email, of course, because I sent it there. Because again, I just couldn't upload this stupid thing to Blackboard. And it was just kept giving me this error. Like it's like something's wrong with the file. I don't remember what it was at this point. So I just couldn't upload it, which is why I had to send it to you. But the exam is available for you now. I uploaded it last night. It released last night. You have until Friday to do it. This is the format. It is a 2-hour time limit. And if you do need accommodations, please remind me. I forget who it is at this point. And I go back to my emails, but I feel like it's easier if you just send me an email to remind me. But other than that, it's a pretty straightforward exam. If you took your exam today, you'd have your grade tomorrow. I did send it last night, Megan. Yeah. If you do take your exam today, I'll grade it as fast as you can. You won't be able to see the feedback on your exam until Friday. Shoot, I keep doing that. You'll be able to see your feedback on your exam until Saturday, just to let you know, because it's locked out until Saturday for you guys to see it, but you'll get your grade. So you'll have an idea of how you did on the exam. But again, you'll see your feedback on Friday, just because, again, I don't want you to be able to share your exam answers with someone. That's not fair to the people who took it blind, right? But other than that, that's the sort of things you should be thinking about. As I said, the biggest hints I gave you to the sort of the things you need to study most is it's mostly climate change. I would say it's about 60 to 70% climate change, just as a note. So that's the thing you want to really focus on. There are no essay questions. You're not getting any information beforehand. So just as a reminder, and I told you one of the short answers is about climate change and the other one's about plastic. And so I told you for one of the short answers, you should also remember to just study up on one particular issue of climate change. Like what's one effect of climate change? Just don't choose sea level rise. Just telling you that now. You can pick invasive species. You can pick diseases. But pick one topic, learn a lot about it. That'll be very helpful for your short answer question. Just telling you now. That's it. That's all I got for you. So I'm going to stop recording because I don't have anything.